Hi and welcome to the second session of our Simulation for Makers workshop series. I'm very glad to see so many of you participating today, the second session. And yes, I think some of you already know the procedure. Before we will actually start to talk about the subject of today, I would just like to make sure that everybody can hear me loud and clearly. So please click the raise your hand button in the case you can hear me. And then I know that everything works fine. Oh great, I see already some hands. In the case audio should not work for you during the session, or if you get any troubles with the audio, you can also use our toll-free audio service numbers, which you can find here on the slide. Just dial these numbers, which are absolutely for free, and then use this access code to join the audio of the session. Yes, today we have our second session, as I mentioned, and we will talk about different aspects of structural simulation. We will talk about vibrations and how to simulate them. And later on, I will show you why we want to do such simulations. Basically, it's just all about reducing vibrations, which can have a very negative impact on your product's performance. Yes, like last week, first of all, I will just summarize the most important things about this webinar, because we have some people who joined for the first time this week. Then I will give you introduction to vibration simulation or structural simulations in general. I will do a live demonstration and show you how you can do this simulation yourself, and then we will talk about the homework, and also for sure we'll have a lot of time for your questions and my answers. Yes, just to make sure everybody knows what we're going to do today, the idea of this workshop is that we from SimScale want to share with everyone who's interested in designing or making his own product our knowledge about simulation. We want to show you very hands-on and insights about engine simulation, and we will help you to gain your first own experience. And really the idea of this workshop is that after attending all 3 sessions and submitting all 3 homework assignments, you will be able to use SimScale for your own ideas and your own designs. And therefore, we cannot talk a lot about fundamentals and theory. So if you're interested more about the math of simulation or which algorithms are used, maybe this webinar is not perfect. But the good thing is you can win or qualify for a pre-professional training, which will also be about fundamental stuff, just by submitting your homework. Okay, then I would say maybe just one thing about the homework. We have already a lot of submissions from last week, so after every session you have like 1 week time to submit a homework assignment, which is in the end about creating a simulation. For this you will also be provided with hands-on tutorials, and you can share this homework using a form on simscale.com. Great, then let's just jump into our live demo / introduction to frequency simulations and harmonic simulations in general. And first of all, I would like to ask you to take a look at these 4 pictures. And here you can see different products. But one thing which they all share is the fact that all these products are in the end driven by vibrations. Let's take a look. For example, here we have a pendulum clock. This pendulum is oscillating from left to right and back, and every time it is passing this median point, this point here, your clock is going forward. And in the end, the frequency of this pendulum is 1 second. All we have here, we have a swing, which is also a very, very good example for vibrations and stuff like that, where in the end, people or the guy on the swing is doing an oscillating movement, and this is gonna to accelerate him and move the whole swing. Or maybe some of you are interested in music, and in the end, a guitar or the string of a guitar is also a vibrating object. When you hear a sound like an A, it is in the end that means that I think A is, for example, at I think 220 hertz. megahertz, and this is the same frequency the string of the guitar is vibrating. Or maybe some of you know this old video of this bridge with this collapsing because a troop is going over it. And this is the same effect, like when you have a part which vibrates, it can also start to vibrate more and more. And all these things in the end are covered by frequency analyzers and harmonic analyzers. And in the end, the idea of all vibration-related simulation on SimScale is that you can, first of all, every physical body has this so-called eigenfrequencies and eigenmodes. These are eigenfrequencies are frequencies which are very important, because when you are gonna to apply a frequency or a periodical load on an object with the same, when the frequency of your load is the same frequency like the eigenfrequency of this part, you will have a lot of effects which can have also negative impact on your product. And one good example is the bridge. The soldiers were walking over this bridge with the same eigenfrequency like the eigenfrequency of the bridge. And this result of this is resonance, which means the amplitude of this vibration becomes higher and higher, because this eigenfrequency is the frequency where you can easily add energy to the system. So at eigenfrequency, an object which is will get a lot of energy, and so the amplitude will become higher and higher, and that's the reason why the bridge in the end crashed. And we have also harmonic analyzers on SimScale, which gives you the physical reactions through the application. And now I think that's a very important point. You need both of them. The first step is doing a frequency analysis, because the frequency analysis will tell you where are the critical eigenfrequencies and eigenmodes, and then you can use these results, these frequencies you get, for the harmonic analysis to calculate in a second step what happens at the eigenfrequencies for a defined periodic oscillation or load. And you may ask yourself, why are we talking about guitars and bridges when it's a workshop for makers? And I think this slide or this image will answer your question. Let's take a look at this. This is a so-called ReRap 3D printer. ReRap is a project which is about designing, building, and sharing 3D printers which can produce themselves. So here you can see, I think it's called Mandel. It's one of the most famous ReRap printers. And in the end, it's just made from standard parts like bolts, nuts, etc. The engines, which you sure have to buy, the step engines, and everything else which is connecting the parts, it's made from ABS. It's printed by a printer. And if you now take a look at the whole printer and then at the frame, you can see here in red all step engines. And the step engines in the end are moving also, or with a defined frequency. And basically a very big problem in manufacturing, not only for 3D printing, also for milling, but is that vibrations can result in a better product quality. Because just imagine, if this frame starts to vibrate, everything is moving, so also the head of the printer, the extruder, and when the extruder is also vibrating, this will make it very difficult for you to control the position and therefore to ensure the right setup of the different layers when your part is printed. And so the idea is, or what we will do right now, is to investigate what the eigenfrequency of this frame is and what happens if, for example, a step engine is operating with such an eigenfrequency. If you would do it, let's say, on a very, very professional level, you would really simulate the whole printer. But as I mentioned, the idea of this webinar is to give you some hands-on insights, and therefore we will just take a look, first of all, at one of these parts of the frame, just to, you will see later why, just to reduce the amount of work, because in the end the learning is the same. And what we will do right now is, or what we'll show you, we will right now perform a frequency analysis of this subframe. So we'll investigate what are the eigenfrequencies and the related eigenmodes of this part. And then we will investigate for several of these identified eigenfrequencies how the frame would react through the application of periodic oscillations. By the way, because I just saw, there's one question. Bradley said, or asked if we have not done the homework for session 1, if it's still possible to qualify for the free training. Bradley, maybe just in general. Basically, we had a deadline. In the case you were not able to submit your homework before, just reach out to me and I'm quite sure we'll find a solution. But in general, you need to submit all homeworks at the right time to get qualified for the free training. And by the way, it's really not hard. You have a very good step-by-step tutorial, and if you have any problems or questions, me, my colleagues, or other community members will be very glad to help you. Okay, now let's take a look at what we exactly want to simulate, because this is a very important point, and this is a really important point in general. Every time you're going to set up a simulation, first of all, you should ask yourself, what is the most efficient, the best way to model my problem? And now let's take a look. So let's say this is our subframe. And if we take a look at this isolated part, there are some things we should consider. First of all, basically it's a symmetric part. So if you take a look back, in the end, this whole frame is made of two of these sub-assemblies which are connected through rods. And therefore, we also have to consider this in our simulation later on. So the first thing is that here we have a kind of symmetric boundary condition. So everything what happened here have to happen exactly on the same side. And also that we cannot have like banding here. It would just physically not be possible, because if we would have banding, a very strong banding here, would not be any collect, and therefore we need a boundary condition to specify that this is half of the part or symmetrical model and apply it later on. Also, this part, this assembly needs to be connected somehow to the ground. Therefore, the easiest thing is just to say this lower surfaces of which are touching the ground cannot move in any direction. But beside of this, we have a much bigger problem. If you remember last time, where we simulated or we did a structural strength analysis of this drone arm, we had one solid. We had like only one body. And right now we are facing with a problem that we have a geometry which contains in the end 6 different solid bodies. Number 1, 2, 3, 4, 5, and 6. And therefore you not only have to define like what is this part made of, which material properties you want to apply, but you have also to consider or to tell the simulation tool how these parts are connected in the end. And this is what we will do right now. We will do it later on also on SimScale, but first of all let's do it just a test and think a little bit. This is a cut through this assembly, and here you can see the structure of the model. So you have on each side one solid where you have fused the nuts and the rod, and you have this connector part which is printed out from ABS plastic. And now in the end, contacts are just defining how the assembly should perform or how it should behave in the case one part of the geometry is deforming or moving. And if we take a look here, we have first of all a contact here between the inner surfaces of this connector and the outer surface of the rod. We have the same on the other side. And if you think right now, it seems to be defined, so we cannot tilt it, but what we could do, we could move it along this axis still. And therefore we need a third contact which is connecting the lower surfaces of the nuts to the surface of this connector. And this, guys, is a very, very important point, maybe the most important point. And defining the context, it needs a lot of experience sometimes, because it's not like a black or white solution. It's more like an approach you have to find. For example, here, you could also ask, is it really correct to fuse the nuts and everything and the rods to one part? I think no. It's not 100% correct, and it will have definitely impact on our results. But from my experience, I know that the impact will be very, very small. And therefore, I decided to fuse these parts, because that will reduce the number of contacts which they have to find. Right now, we have 9 contacts. If we would not fuse it, we would have like more than 50 contacts in the end, maybe. And that's a question you have to face with every time. So, and there's a general rule: as much contacts as really necessary and as less as possible. But I think you knew this rule from other things. And right now what we will do is we will open a project which contains the CAD model of the subassembly of the frame. We will first of all create the mesh like last time. So we will divide the volume of this body into smaller subvolumes, which are later on then used to calculate in this cells stress, displacement, etc. Or in our case, not in the cells, but at the nodes. If this is finished, we can start to set up the simulation. That means we have to define materials, etc. And then we can do post-processing and take a look at the result. And again, this is very important. In this case, we will not get, we will get some fancy, colorful pictures, but what we are looking for in the end is only a list with the eigenfrequencies, but you will see this just in some minutes, what I mean. Okay, let's start. I've for sure prepared something.
I've just opened several tabs, and yes, let's start. First of all, I will open this project. This project link will later on also send to you, and it includes the geometry of the part of the chart we want to investigate. And yes, you can for sure also theoretically upload your own CAD model using this button, this upload geometry menu. But we will now yes, mesh this as the first step. And what you can see, we have this model is made out of 6 different solid bodies. We have 3 solids, including the rods and with the nuts and the washers, and 1 solid per each plastic connector. And first of all, what we can check if we take a look at this model here is, for example, the bounding box length, which is nearly 1/2 meter, and that is just a good indicator for us that conversion worked at this in the right scale. Yeah, now let's create the mesh. Click the Create Mesh button to create a new mesh project. Then select the base, so the geometry you want to use or which you want to mesh. In this case, we only have 1 geometry, so save. Then this model will also be associated with this matching job, and you can see it then also here in the 3D menu. Now we have to add the mesh operation, and we will again use the fully automatic tetrahedralization and use the same settings like last time. So we will do it first order, since first order meshes are less memory consuming, and we don't need a second order mesh for this easy simulation later on. We will make a moderate mesh from the finest level and use 4 processors. Just save, press the start button, and then you go and the mesh will be generated in the next 10 minutes. To save a little bit of your time, I've already prepared another project, including this finished mesh. So it's the same geometry, the same settings. I just started the meshing process earlier. And yes, the final mesh will look like this. And as you know from the last time, this mesh is intelligent, so it's automatically refining the mesh in the near of small faces and edges. And again, we have 6 subvolumes of elements in this mesh. So this is exactly like last time. For every solid, there is a own element group. Okay, let's do the quick wrap up. I just showed you how to upload a CAD model, or in this case, how to open and import a project. Then we performed automatic t-driddle meshing with the parameter for fineness of 3, which is moderate, and a first order mesh. An advanced topic here would be everything related to manual mesh setup. For example, you could theoretically choose, instead of this automatic operation, you could also do manual operation with refinements. Another thing we did not cover here, which would be advanced, is CAD cleaning and preparation, which was here again some work. I mean, this separating this part out of the whole assembly and fuse the nuts and the washers to the rod, and also mesh quality assessment. As I mentioned, meshing is not only about doing the mesh or dividing, it's also about quality of the mesh. So there are specific criteria as how the mesh should look like from a structure. And this is something which can become a problem for very complex geometries and very complex simulation. In this case, not necessary. By the way, you get also a kind of feedback and everything is worked right in this mesh operation. Okay, next step then is to set up the actual simulation. We will therefore switch to the simulation designer. Create a new simulation by clicking this button here, new simulation. You can identify it by this plus sign. And then we are guided to this menu where we can choose what kind of simulation we want to perform. In this case, it's a solid mechanics simulation and it's a frequency analysis. And there are no sub options, so we can just click on save. Then SimScale will build up this tree, and going through this tree will help us to set up the simulation. So we are guided through the simulation. Everywhere you see this red bubble, it means that there is something which is mandatory is missing. For example, the mesh. We will use only mesh we have. Now it becomes also green. Next thing is not red, but it's also very important. It's called contacts. It's came just new, this part of the tree. And as we discussed, we need contacts. And there are two opportunities. You could also first create this phase groups entity sets and then create the contacts out of them. This is maybe a little bit more comfortable if you want to do a lot of changes later on, but since we want to make it faster and very easy, we'll do it directly. And we'll now just do 3 contacts do contacts from around one of these plastic connectors to show you how it's working from principle. So let's start with add a new contact, and we will now focus only on this connector. This is body 3, so we can turn out the other ones, and we can also turn off this one. Okay, and let's start with this contact. So let's call it contact 3 for body 3 and 0 for the number for the first contact. So we count 0, 1, 2. That's the engineering thing. And yes, as you see, contact 0 is between the cylindrical face of the rod and the hole of the connector. 1 is the same thing on the other side, and yellow is connecting the washers, or the connect between the washers and the connector, the plastic connector. Then let's switch back and start. And now a lot of people asked me last time, where do I know if a face is master or slave? And for this, there are no very complete static rules, and it's not like that. Sometimes it's even makes no difference. But in general, you should make the master, you should choose the faces for master which are moving the less and which are bigger. And in this case, therefore, we will use as a master in general, the connectors, and as a slaves, the other parts which are connected. So let's start. And the easiest thing is for the first contact to define it. And we will now pick that faces here, which is our master first, or just lost the name, contact 3, 0. And the corresponding slave faces are these 2. Select them here. Great. And we can save it now. This is exactly the same thing with the next contact. Contact 3, 1. Our master faces are this one and for the slave we have these 2 faces. And then finally, maybe the most complex contact of all. And here we need now everything, so the master surfaces. We're talking now about the washers with this connector. So if you want to take a look again about this contact 2, this yellow one, this are the master faces. And we have also here the slave faces. And now save. We will need at least 9 contacts, so 3 contacts for the other 2 connectors. But since that will just take a lot of time and it's exactly the same procedure, I will just skip this. Next thing we have to do is to define and add materials. So we can just take steel of a library for all parts which are from metal. So this through bodies. And, oh, my fault. First select, then add, then save. And we have to assign a material to these connectors which are printed out of ABA plastic. So let's call it ABS. Add the correct material properties. Don't forget you will get a step-by-step tutorial later on where you get all these numbers, and then select the 3 parts. Great, and now the only thing which is missing which are missing our boundary conditions. And that's again therefore skip back in the slides. We have a fixation in one direction, in that direction for the foods here. And we have a fixation all directions for the 6 holes. Start. Change selection mode to faces first. Add the new one. Then select these 2 faces here. And just call it maybe floor. And we want to only to prescribe that direction. And this is done now. Let's do the same for the other rods or the holes. And here everything is fixed. And we have to select them all now. Okay, here we go. Great. And this is done. Yeah, so now finally we don't have to change any numerics, we don't have any preload, and now we have just to do the simulation control. And we have here, this is okay, the maximum runtime and the number of computing cores. And then we have to say how many eigenfrequencies want to be calculated, let's say 20 for example, and we have to define the lower and the upper frequency limit, which is investigate. So we will now only investigate the first 20 eigenfrequencies which are in this range. And 0 to 100,000 is too much. We have just calculated for a standard step engine for all operating modes, it should be between 1,000 and 10,000 Hertz. Great. Now there's nothing to do. We can just check the simulation. We will get a warning. It's more a warning, it's not critical, just saying so let's using is not completely working in parallel. Then we can create a new run and start the simulation, which I will not do right now since contacts are missing. But if you would add the missing contacts, what we can just do right now, or we will not do it, but if you add the contact and start the simulation run, then you get a result which I've prepared. And the result will look like this. Let's open it. And maybe first of all, yes, if you then here have added all contacts, and then when your simulation is finished, you get a notification. Okay, let's just do a quick wrap up. I showed you how to, or I explained again what topological entity sets are. I showed you how to define the 3 types of contacts you need for the simulation. We defined together the material. For this, we imported one material model for steel out of the material library and created a new material model ourselves using the material properties of ABS. And then we assigned the boundary conditions for the fixation and adapted our solver settings. Right, and when this is done successfully, you can switch to post-processor, and then you can check out 3 things. In contrast to our thermal simulation, we are working more with numbers here on tables. So you can, for example, get first of all inside what are the eigenfrequencies and what are of this chassis. So we have a table here, and you can see here I've calculated 51, and you can see them here, and you can also have a plot, and you see these are all frequencies which will be critical for 5,233 hertz or 4,800 hertz, and between this, like here, it would be better. To wrap this up, yes, I showed you just how to access the results. It's maybe a little bit confusing that it's not so visual as the other ones we did, but this is, as you know, just the input for the later analysis. And then I would like to discuss the homework with you. So your homework will be for this week to create the frequency analysis from scratch. You will therefore be provided with this project, including the models and a step-by-step instruction. It's exactly the same procedure like I showed you right now. And then you are asked on this next level to create a harmonic analysis based on these results. How the mesh, you can reuse the mesh for this, so you don't have to create a new mesh. And you have just to adapt some small things. And we will also provide for this a step-by-step instruction. Okay, great, guys. Thank you very much for your time. It was a big pleasure. And yes, right after that, we have time for some questions. And yes, thank you very much also for your homework submission so far. Have a nice weekend. And yes, hope to see you next week. Bye.